For centuries, humanity looked up at the river of light stretching across our night sky and wondered, just how vast is our cosmic home? Well, prepare to have your mind completely blown. Scientists have just discovered that the Milky Way is far bigger, more massive, and more extraordinary than we ever imagined. Using revolutionary data from the Gaia Space Telescope and breakthrough observations from telescopes around the world, we've learned that our galaxy isn't just large, it's a behemoth that defies our previous understanding. What we found changes everything about our place in the universe. If you're fascinated by cosmic discoveries and want to explore the universe's greatest mysteries with me, make sure to subscribe to this channel and give a thumbs up. Now let's begin. The story of discovering our galaxy's true size begins with a spacecraft that's revolutionizing astronomy. Launched in 2013 by the European Space Agency, Gaia isn't your typical space telescope. Instead of taking pretty pictures, it's conducting the most ambitious survey in astronomical history, creating a three-dimensional map of over 2 billion stars. That's right, 2 billion stars, each one precisely measured for position, distance, and motion. It's like going from a rough sketch of your neighborhood to a detailed GPS map of an entire continent. But here's where things get absolutely mind-blowing. When scientists analyzed Gaia's latest data release in 2022, combined with observations from ground-based telescopes in Chile, Hawaii, and Australia, they discovered something shocking. The Milky Way's stellar disk, the flat spinning region where most stars live, including our Sun, extends out to at least 100,000 light-years from the galactic center. Previous estimates put it at around 80,000 light-years. That's a 25% increase in diameter, which means the area of our galaxy's disk is over 50% larger than we thought. To put this in perspective, light, the fastest thing in the universe, racing at 300,000 kilometers per second, would take 100,000 years just to cross from one edge of our galaxy to the other. If you started that journey when modern humans first began migrating out of Africa, you still wouldn't have made it across. The scale is so vast that our brains literally can't comprehend it without breaking it down into smaller pieces. But the stellar disk is just the beginning. Surrounding it is something even more spectacular, the galactic halo. This roughly spherical region contains ancient stars, globular clusters, and mysterious dark matter. Recent observations from the Dark Energy Survey and the Subaru telescope in Hawaii have traced this halo out to distances that seemed impossible just a few years ago. We're now detecting stars that belong to our galaxy at distances of over 300,000 light-years from the center. Some research even suggests the halo might extend out to 900,000 light-years or more. Think about what this means. If the Milky Way were the size of a dinner plate, the visible disk would be the plate itself, but the halo would be like an invisible sphere the size of a house surrounding it. We live inside something far grander than the beautiful spiral we see in artists' illustrations. We're residents of a cosmic metropolis that dwarfs our previous understanding. The mass revelations are equally staggering. By tracking how stars orbit the galactic center, astronomers can calculate the total gravitational pull and therefore the mass of our galaxy. The latest measurements from Gaia, combined with observations of satellite galaxies orbiting the Milky Way, put our galaxy's total mass at around 1.5 trillion times the mass of our Sun. That's trillion with a T. Previous estimates ranged from 700 billion to 1 trillion solar masses, so we're talking about an increase of at least 50%. But here's the kicker. Only about 60 billion solar masses of that is from stars we can see. Another 60 billion comes from gas and dust. The rest? That's dark matter, the mysterious invisible substance that makes up most of the universe's mass. Our galaxy is literally held together by something we can't see, can't touch, and barely understand. It's like discovering your house has rooms you never knew existed, filled with furniture you can't perceive, but that affects everything around it. The discovery process itself reads like a detective story. Astronomers didn't just point telescopes at the sky and suddenly realize the galaxy was bigger. They had to piece together clues from multiple sources. Red giant stars in the galactic halo acted as standard candles, their predictable brightness allowing distance measurements. RR Lyrae variables, pulsating stars with precise period luminosity relationships, served as cosmic mile markers. And the motion of satellite galaxies like the Large and Small Magellanic Clouds revealed the gravitational influence of mass we couldn't directly observe. One of the most stunning revelations came from studying stellar streams, the ghostly remnants of smaller galaxies that the Milky Way has torn apart and consumed over billions of years. The Sagittarius stream, discovered in 1994 and mapped in detail by Gaia, wraps around our entire galaxy multiple times like a cosmic ribbon. This stream alone contains hundreds of millions of stars that once belonged to the Sagittarius dwarf galaxy, now being slowly digested by our cosmic home. Following these streams has revealed that our galaxy's gravitational influence extends much farther than anyone anticipated. The technology behind these discoveries is nothing short of miraculous. Gaia measures stellar positions with an accuracy of 10 micro-arc-seconds. That's like being able to see a human hair from 1,000 kilometers away. It tracks the tiny wobbles and movements of stars across years, building up a dynamic picture of our galaxy in motion. Every star becomes a test particle, revealing the gravitational landscape it moves through. It's as if we've gone from studying a photograph of a city to watching a time-lapse video of its entire history. But perhaps the most humbling discovery is about our galaxy's future interactions. The Milky Way isn't just big, it's getting bigger. Right now, as you watch this video, our galaxy is pulling in gas from the Magellanic Stream at a rate of about 1 solar mass per year. That might not sound like much, but over billions of years, it adds up to hundreds of billions of stars worth of material. We're living in a growing, evolving cosmic ecosystem that's constantly refreshing itself with new material. Speaking of our galaxy's vastness and our place within it, if you're curious about why we might be forever bound to this cosmic island despite all our technological advances, check out my video called "This is Why We Will Never Leave the Milky Way." The sheer scale we're discussing today makes that reality even more profound. The link is in the description and on the card above. The vertical structure of our galaxy has also surprised astronomers. The disk isn't flat like a pancake, it's warped and twisted, especially at its outer edges. Imagine a vinyl record that's been left in the sun and warped. Data from Gaia and infrared observations from NASA's WISE mission show that one side of the disk curves up while the other curves down, and this warp actually rotates around the galaxy like a wave, completing one rotation every 400 to 500 million years. Even more fascinating is the discovery of the galaxy's thick disk, a population of older stars that extends above and below the main thin disk where our Sun resides. This thick disk reaches heights of about 3,000 light-years above and below the galactic plane. It's like discovering your single-story house actually has a previously hidden second floor and basement. These stars tell the story of our galaxy's violent past, when smaller galaxies crashed into the young Milky Way and puffed up part of its disk. The spiral arms themselves have revealed new secrets. Using infrared telescopes that can peer through cosmic dust, astronomers have confirmed that our galaxy has 4 major spiral arms, not 2, as some models suggested. These arms, Perseus, Sagittarius, Carina, Scutum Centaurus, and Norma, are density waves where stars and gas pile up, triggering bursts of star formation. Our Sun sits in a minor arm called the Orion Spur, about 26,000 light-years from the galactic center. The precision of these measurements has revealed something extraordinary about our cosmic neighborhood. The local bubble, a region of hot, low-density gas surrounding our solar system, extends for about 1,000 light-years. We now know this bubble was created by a series of supernovae over the past 14 million years. We're literally living inside the aftermath of stellar explosions, protected by this cosmic cavity from some of the harsher radiation that permeates other parts of the galaxy. Recent discoveries about the galactic center have been equally revolutionary. The supermassive black hole at our galaxy's heart, Sagittarius A star, weighs in at 4.3 million times the mass of our Sun. But here's what's incredible. Despite this monstrous mass, it's remarkably quiet compared to black holes in other galaxies. The Event Horizon Telescope collaboration, which gave us the first image of a black hole, is now working on imaging our galaxy's central black hole, promising even more revelations about the dark heart of our cosmic home. The distribution of different stellar populations tells the story of our galaxy's evolution. The oldest stars, formed over 13 billion years ago when the universe was just a baby, lurk in the halo and globular clusters. These ancient suns contain hardly any elements heavier than hydrogen and helium. Younger stars like our Sun, rich in heavier elements forged by previous generations of stars, populate the disk. It's like reading tree rings, but instead of telling us about seasons and years, these stellar populations tell us about eons and epochs. One of the most exciting developments is our understanding of the galaxy's dark matter halo. While we can't see dark matter directly, its gravitational effects on visible matter reveal its presence. The latest models suggest our galaxy sits inside a roughly spherical dark matter halo that extends out to at least 600,000 light-years, possibly much more. This invisible scaffolding contains over 90% of our galaxy's total mass. We're essentially living inside a ghost galaxy that dwarfs the visible one we see in our telescopes. The velocity measurements from Gaia have unveiled another shocking truth about our galactic home. Stars at the outer edges of the Milky Way are moving far too fast to be held by the gravity of visible matter alone. They should be flying off into intergalactic space, but they're not. This was one of the first clues to dark matter's existence decades ago, but now we can map it in unprecedented detail. The rotation curve of our galaxy, how fast stars orbit at different distances from the center, reveals the invisible hand of dark matter holding everything together. What really boggled astronomers' minds was discovering how dynamically complex our galaxy is. It's not just spinning like a simple wheel. Different components rotate at different speeds and sometimes in different directions. The central bar, yes, our galaxy has a bar-shaped structure at its core, about 27,000 light-years long, rotates like a solid object. The spiral arms are density waves moving at their own pace. The halo barely rotates at all, with some parts even moving retrograde, opposite to the disk's rotation. It's choreographed chaos on a scale that defies imagination. The chemical composition mapping has revealed that our galaxy is like a cosmic layer cake. Elements heavier than hydrogen and helium, what astronomers call metals, are distributed in gradients throughout the galaxy. The inner regions are metal-rich, products of billions of years of stellar evolution and supernovae. As you move outward, the metallicity drops. This gradient isn't smooth, though. It shows bumps and variations that tell stories of ancient collisions and star formation bursts. Each region has its own chemical fingerprint, a unique mixture that reveals its history. One profound discovery is the galaxy's fossil record, ancient stellar structures that preserve the memory of long-ago events. The Gaia sausage, despite its amusing name, is the remains of a massive dwarf galaxy that collided with the Milky Way 8 to 10 billion years ago. This collision was so violent it completely reshaped our galaxy's halo and thick disk. The stars from this ancient galaxy still move together in a characteristic pattern, like ghosts dancing to music only they can hear. The number of satellite galaxies orbiting the Milky Way keeps growing as our detection methods improve. We now know of at least 60 dwarf galaxies bound to our own, with more being discovered regularly. The large and small Magellanic Clouds are just the most famous. Others, like the Draco Dwarf, Fornax Dwarf, and Sculptor Dwarf, are so faint that they're invisible to the naked eye despite containing millions of stars. Each one is slowly being torn apart by our galaxy's gravity, their stars eventually joining the Milky Way's halo. The interstellar medium, the space between stars, turned out to be far more complex than anyone imagined. It's not empty but filled with gas and dust organized into intricate structures. Giant molecular clouds, some containing millions of times the mass of our Sun, serve as stellar nurseries. Superbubbles blown by stellar winds and supernovae create cavities hundreds of light-years across. Magnetic fields thread through everything, channeling gas flows and affecting star formation. The galaxy isn't just a collection of stars, it's a living, breathing ecosystem. Recent observations have detected high-velocity clouds, massive clumps of gas moving at speeds that don't match the rotation of the disk. Some of these clouds are falling into the galaxy from intergalactic space, bringing fresh fuel for star formation. Others might be gas-stripped from satellite galaxies, or even material expelled from our own galaxy by ancient supernovae, now falling back down. These clouds contain enough gas to form millions of new stars, ensuring our galaxy's stellar population continues to grow and evolve. The age distribution of stars tells an incredible story of cosmic evolution. The oldest stars in our galaxy formed just 200 million years after the Big Bang, when the universe was only 2% of its current age. These ancient suns have witnessed almost the entire history of the cosmos. Meanwhile, new stars are being born right now in stellar nurseries like the Orion Nebula. Our galaxy creates about 2 new stars every year, a rate that has remained surprisingly steady for billions of years. The discovery of hypervelocity stars added another dimension to our understanding. These stellar speedsters are racing through the galaxy at velocities exceeding 1,000 kilometers per second, fast enough to escape the Milky Way's gravitational pull entirely. Most were probably ejected from the galactic center after close encounters with the supermassive black hole. Tracking these cosmic bullets helps us understand the extreme gravitational dynamics at play in our galaxy's core. What's particularly stunning is realizing how our view of the galaxy has changed with each technological leap. Before radio astronomy, we couldn't see through the dust to map the spiral arms. Before infrared telescopes, the galactic center was hidden from view. Before space-based observatories, atmospheric distortion limited our precision. And now, with Gaia and other cutting-edge instruments, we're seeing our cosmic home with clarity that would have seemed like magic to astronomers just a generation ago. The stellar density variations across the galaxy paint a picture of cosmic architecture on an unimaginable scale. Near the galactic center, stars are packed so densely that if we lived there, the night sky would blaze with the light of 1 million suns. Some regions have stellar densities 1 million times greater than our local neighborhood. Meanwhile, in the outer halo, stars are so sparse that each one is isolated by hundreds of light-years of empty space. The discovery of stellar nurseries throughout the galaxy has transformed our understanding of ongoing cosmic creation. The Carina Nebula, 4,500 light-years away, is churning out massive stars that will live fast and die young in spectacular supernovae. The Eagle Nebula's pillars of creation, made famous by Hubble, are stellar nurseries where gas columns light years tall are collapsing to form new suns. These regions aren't randomly scattered, they follow the spiral arms, creating a pattern of star formation that propagates around the galaxy like a cosmic Mexican wave. One of the most mind-bending revelations is that our galaxy has a habitable zone just like solar systems do. Too close to the center, and the radiation from densely packed stars and frequent supernovae would sterilize any planets. Too far out, and there aren't enough heavy elements to form rocky planets, or the complex chemistry needed for life. We exist in the galactic sweet spot, roughly 26,000 light-years from the center, where conditions are just right for life to emerge and thrive. It's another reminder of how incredibly fortunate we are to exist at all. The magnetic field structure of our galaxy, invisible to our eyes but revealed by radio telescopes and polarized light observations, is absolutely mesmerizing. These fields stretch across thousands of light years, channeling cosmic rays and affecting how gas clouds collapse to form stars. The field lines follow the spiral arms but also extend vertically above and below the disk, creating a complex three-dimensional web of magnetism. It's like discovering that our cosmic city has an invisible infrastructure of force fields shaping everything within it. Recent studies of variable stars, stars that pulse, flare, or change brightness in predictable ways, have given us a new cosmic measuring tape. Cepheid variables, RR Lyrae stars, and Mira variables each provide different ways to gauge distances across the galaxy. By combining these different standard candles, astronomers have created a three-dimensional map accurate to within a few percent. It's like having GPS satellites scattered throughout the galaxy, each broadcasting its precise location. The phenomenon of galactic fountains has added another layer to our understanding. Hot gas from supernovae rises above the galactic disk, cools, and then falls back down like a cosmic fountain. This cycle, taking millions of years, mixes elements throughout the galaxy and regulates star formation. Radio telescopes have detected these fountains extending thousands of light years above and below the disk. We're not just living in a static galaxy, we're part of a dynamic system with circulation patterns that dwarf anything on Earth. The discovery of the galaxy's co-rotation radius has special significance for our existence. This is the distance from the center, where stars orbit at the same speed as the spiral arms themselves. Inside this radius, stars move faster than the arms and regularly pass through them. Outside, they move slower and also cross the arms periodically. But at the co-rotation radius, stars stay between spiral arms for billions of years. Our Sun orbits very close to this special radius, meaning we avoid the dangerous spiral arms where massive stars form and die in supernovae. Another cosmic coincidence that makes our existence possible. Analysis of stellar metallicities has revealed waves of star formation that swept through our galaxy's history. These weren't steady processes but came in bursts, likely triggered by collisions with other galaxies or the infall of fresh gas. The most recent burst occurred about 1 to 2 billion years ago, possibly triggered by a close encounter with the Sagittarius dwarf galaxy. These waves of star formation enriched the galaxy with heavier elements, each generation of stars building on the ashes of the previous one. The outer reaches of our galaxy hold surprises that challenge our models. Stars have been found at distances where they shouldn't exist according to traditional galaxy formation theories. Some appear to be moving in orbits that suggest they were captured from passing galaxies. Others might have been flung outward by gravitational interactions in the galaxy's youth. These stellar outliers are rewriting our understanding of how galaxies grow and evolve. The discovery of the Radcliffe wave in 2020 stunned the astronomical community. This is a massive, wave-like structure of stellar nurseries stretching 9,000 light-years, undulating above and below the galactic plane. It's the largest coherent structure ever found in our galactic neighborhood, and we're actually inside it. The Sun passed through this wave about 13 million years ago and will encounter it again in another 13 million years. Imagine discovering that your neighborhood is part of a massive wave frozen in time and space. The interaction zones where our galaxy meets intergalactic space are particularly fascinating. The boundary isn't sharp but fuzzy, with streams of gas flowing in and out. The Magellanic Stream, trailing behind the large and small Magellanic Clouds, extends for over half the way around the sky as seen from Earth. This isn't just a pretty cosmic ribbon, it's an active pipeline bringing fresh gas into our galaxy, fuel for future generations of stars. Dark matter subhalos, smaller clumps of dark matter within our galaxy's main halo, have been indirectly detected through their gravitational effects on stellar streams. These invisible structures, some containing as much dark matter as a dwarf galaxy but no stars at all, roam through our galaxy like cosmic ghosts. They occasionally pass through the disk, potentially triggering bursts of star formation or disrupting stellar orbit. We're living in a galaxy haunted by invisible giants. The vertical oscillations of our solar system through the galactic disk have profound implications we're only beginning to understand. Like a horse on a cosmic carousel, we bob up and down through the disk's midplane every 64 million years. Some scientists have proposed this cycle might correlate with mass extinction events on Earth, as our passage through denser regions exposes us to more cosmic rays and potentially disturbs the Oort cloud, sending comets toward the inner solar system. We're not just orbiting the galaxy, we're surfing through it in a complex dance that affects life itself. One of the most spectacular recent discoveries is the Fermi bubbles, gigantic structures of hot gas extending 25,000 light-years above and below the galactic center. Detected in gamma rays by NASA's Fermi Space Telescope, these bubbles are evidence of a massive explosion or outburst from our galaxy's central black hole millions of years ago. It's like finding out that the quiet neighborhood you live in was once the site of a cosmic volcanic eruption that reshaped everything around it. The chemical evolution of our galaxy reads like a cosmic cookbook. First-generation stars contained only hydrogen and helium from the Big Bang. When they died, they created the first carbon, oxygen, and other elements. Each subsequent generation of stars has cooked up heavier elements in their nuclear furnaces. By the time our Sun formed 4.5 billion years ago, the galaxy had been enriched with all 92 naturally occurring elements. The calcium in your bones, the iron in your blood, the oxygen you breathe, all were forged in the hearts of dying stars scattered throughout the Milky Way. Stellar archaeology, the study of the oldest stars to understand the galaxy's past, has revealed that our galaxy formed through a chaotic process of mergers and acquisitions. The chemical signatures of ancient stars show at least 5 major accretion events in the Milky Way's early history. Each merger brought in stars with different chemical compositions, orbital patterns, and ages. We can still see these ancient populations today, like finding artifacts from different civilizations layered in an archaeological dig. The discovery of blue stragglers, stars that appear younger than they should be, adds another mystery to our galactic story. These stars shine hot and blue like young stars, but exist in ancient globular clusters where star formation ceased billions of years ago. They likely formed from stellar collisions or by siphoning material from companion stars, essentially getting a cosmic facelift. They remind us that even in a galaxy 13 billion years old, renewal and rebirth are possible. The galactic ecosystem extends far beyond stars and gas. Cosmic rays, high-energy particles accelerated by supernovae and other violent events, fill the galaxy, creating a sea of radiation we're constantly swimming through. Earth's magnetic field protects us from the worst of it, but these particles affect everything from cloud formation to DNA mutations. The cosmic ray density varies throughout the galaxy, creating regions more or less hospitable to life. We exist in a relatively calm cosmic ray environment, another factor in our unlikely existence. Recent observations have revealed that our galaxy is surrounded by a circumgalactic medium, a vast atmosphere of hot gas extending hundreds of thousands of light-years in all directions. This gas, heated to millions of degrees, contains as much mass as all the stars in the galaxy combined. It's the reservoir from which the galaxy draws new material and into which dying stars expel their enriched guts. Think of it as the galaxy's respiratory system, breathing in fresh gas and exhaling the products of stellar death. The discovery of ultra-faint dwarf galaxies has pushed the boundaries of what we consider a galaxy. Some of these cosmic lightweights contain only a few thousand stars, less than a typical globular cluster. Yet they're embedded in massive, dark matter halos. They're the smallest, darkest galaxies possible, barely held together by gravity. Finding them is like discovering that mountains can be the size of anthills while still being genuine mountains. They force us to reconsider what defines a galaxy. Tidal streams crisscrossing our galaxy tell tales of cosmic cannibalism on a grand scale. The Orphan Stream, the Helmi Stream, and dozens of others are the shredded remains of galaxies consumed by the Milky Way. By rewinding their motions, astronomers can reconstruct when and how these galaxies were destroyed. It's cosmic forensics, solving murders that happened billions of years ago. Each stream is a gravestone marking the death of a galaxy and the growth of our own. The asymmetries in our galaxy challenge the simple picture of a perfect spiral. The disk is lopsided, with one side containing more stars than the other. The spiral arms have different strengths and shapes. The bar at the center is offset from the geometric center. These imperfections aren't flaws, they're evidence of our galaxy's dynamic history and ongoing evolution. Perfect symmetry would mean stagnation. Our galaxy's asymmetries show it's alive and changing. The discovery of phase spirals in stellar motions revealed by Gaia data shows that our galaxy still bears scars from ancient impacts. These are patterns in how stars move vertically through the disk, created when something massive, probably a dwarf galaxy, punched through the disk hundreds of millions of years ago. The stars still slosh up and down from that ancient collision, like ripples in a pond that never quite fade away. We're living in the aftermath of cosmic collisions that predate complex life on Earth. The molecular cloud complexes scattered throughout our galaxy are nothing short of cosmic cities where stars are born. The Orion Molecular Cloud Complex, the nearest star-forming region to Earth at about 1,400 light-years away, contains enough material to form tens of thousands of stars like our Sun. These aren't just random clumps of gas. They're organized into filaments, cores, and shells by the interplay of gravity, turbulence, and magnetic fields. Each cloud is a potential stellar metropolis waiting to burst into light. What's truly remarkable is how we've detected organic molecules in these stellar nurseries. Radio telescopes have identified over 200 different molecular species floating in space, including ethanol, formaldehyde, and even amino acids, the building blocks of proteins. The galaxy isn't just making stars, it's cooking up the ingredients for life on a massive scale. Every molecular cloud is a cosmic chemistry lab performing experiments that would be impossible on Earth. The phenomenon of galactic winds has reshaped our understanding of how galaxies breathe. Powerful outflows from star-forming regions and active galactic nuclei can drive gas completely out of the galaxy at speeds exceeding 1,000 kilometers per second. But this isn't a loss. Much of this gas eventually falls back, enriched with heavy elements from supernovae. Our galaxy has been exhaling and inhaling for billions of years, each breath mixing and enriching the cosmic atmosphere we live in. The discovery of the galaxy's twisted magnetic field structure revealed yet another layer of complexity. These fields don't just follow the spiral arms, they rise above and below the disk in massive loops, sometimes reversing direction. Pulsars, spinning neutron stars that act like cosmic lighthouses, have helped map these fields by showing how their radio waves are rotated by magnetism. It's like discovering that our cosmic city has an invisible subway system of magnetic field lines running through it. Recent studies of planetary nebulae, the beautiful shells of gas expelled by dying stars, have shown that our galaxy is full of stellar art galleries. Each nebula is unique, shaped by the star's rotation, magnetic fields, and companion stars. The Ring Nebula, the Helix Nebula, the Cat's Eye Nebula. Each one is a masterpiece painted with light and gas. In a few billion years, our own sun will create its own planetary nebula, adding another piece to the galaxy's collection. The galactic bulge, the dense, roughly spherical region at our galaxy's center, turned out to be far more interesting than a simple ball of old stars. X-shaped, when viewed from the side, rotating like a solid bar and containing stars with wildly different ages and compositions, it's a dynamic region where stellar orbits can be chaotic and unpredictable. Some stars zoom through on highly elliptical orbits, diving close to the central black hole before swinging back out to the edges of the bulge. The discovery of stellar voids, regions conspicuously empty of stars, raises intriguing questions. Some voids might be cleared by supernovae or stellar winds. Others might never have formed stars due to turbulence or magnetic fields. The local void, a region near our galaxy with far fewer galaxies than average, affects our galaxy's motion through space. We're not uniformly surrounded by matter, but exist in a cosmic Swiss cheese of dense regions and empty spaces. Globular clusters orbiting our galaxy are like time capsules from the early universe. Omega Centauri, the largest globular cluster visible from Earth, contains 10 million stars packed into a sphere just 150 light-years across. But here's the twist: it's probably not a true globular cluster, but the stripped core of a dwarf galaxy consumed by the Milky Way. Many globulars show multiple stellar populations, evidence of a more complex formation history than we once believed. The interplay between our galaxy and the cosmic web is more intimate than we realized. Filaments of the cosmic web channel gas toward galaxies, feeding their growth. Our local group of galaxies sits in a relatively empty region, which affects how fast we're moving through space and how much intergalactic gas we can accrete. We're not an isolated island universe, but a connected node in a vast cosmic network. The discovery of runaway stars fleeing our galaxy at incredible speeds tells dramatic stories of cosmic violence. Some were ejected from binary systems when their companions exploded as supernovae. Others were flung out by close encounters with the supermassive black hole. A few might even be immigrants from other galaxies, passing through at hyperbolic velocities. These stellar refugees remind us that not everything in the galaxy is gravitationally bound. Some stars are just passing through. The chemical gradient across our galaxy's disk provides a timeline of its formation. The inner regions, enriched by billions of years of star formation, have metallicities several times higher than the outer edges. But this gradient isn't smooth. It shows breaks and features that correspond to the galaxy's spiral arms and past merger events. By measuring the composition of stars at different locations, We can read the galaxy's history like tree rings, each zone telling its own story of stellar birth and death. The role of supermassive black holes in galaxy evolution has become clearer with each new discovery. Sagittarius A star, despite being relatively quiet now, shows signs of past activity. X-ray echoes bouncing off gas clouds reveal that it was much more active just a few hundred years ago. The relationship between a galaxy's central black hole mass and its bulge properties suggests these monsters play a crucial role in regulating galaxy growth, though we're still figuring out exactly how. The discovery of ultra-long period variable stars has given us cosmic clocks that tick over centuries. Mira, variables can have periods exceeding 1,000 days, pulsing like slow heartbeats across the galaxy. By monitoring these stellar timekeepers, we've learned that different parts of the galaxy have different rhythms. The older halo population pulses more slowly and irregularly than the younger disk stars, as if different neighborhoods of our cosmic city keep different time. One of the most profound realizations is that our galaxy operates on multiple timescales simultaneously. Chemical enrichment happens over billions of years. Spiral density waves rotate on 100-million-year cycles. Individual stars orbit in hundreds of millions of years. Star formation bursts last tens of millions of years. Supernovae explode in seconds, but their effects last millions of years. We exist at the intersection of all these different cosmic clocks, each ticking at its own pace. The discovery of blue streams of young stars in unexpected places challenges our models of galactic evolution. These stellar rivers, containing hot blue stars only a few million years old, stretch across regions where star formation shouldn't be happening. Some might be the result of gas clouds colliding at high speed, triggering rapid star formation. Others could be tidal tails from disrupted galaxies, still forming stars as they're stretched across space. They're like finding rivers flowing uphill. They shouldn't exist, but there they are. Recent observations of the galaxy's dark matter wake have revealed we're not alone in feeling the gravitational pull of the Large Magellanic Cloud. This massive satellite galaxy is creating a wake in our galaxy's dark matter halo, like a boat moving through water. This wake affects the orbits of stars and satellite galaxies, creating a complex gravitational landscape that we're only beginning to map. The Milky Way isn't a static backdrop, it's responding dynamically to its largest companion. The phenomenon of galactic archaeology has revealed that different stellar populations remember their origins in their orbital patterns. Stars from the same disrupted galaxy continue to move together billions of years later, creating kinematic groups that astronomers can identify. It's like finding that people from the same ancestral village still walk with the same gait generations later. These stellar families preserve the memory of long-dead galaxies in their motions. The discovery of intermediate mass black holes in globular clusters adds another layer to our galaxy's structure. These black holes, weighing thousands of times our Sun's mass, bridge the gap between stellar mass black holes and supermassive ones. They might be the seeds from which supermassive black holes grew, or remnants of the first generation of stars. Finding them hiding in ancient globular clusters is like discovering medieval castles have secret dungeons we never knew about. The galactic corona, a hot, diffuse gas extending far beyond the visible disk, contains as much mass as all the galaxy's stars. This million-degree gas, detected through its absorption of distant quasar light, is the galaxy's extended atmosphere. It's the medium through which satellite galaxies move, slowly being stripped of their own gas. We're living deep inside this cosmic atmosphere, protected by our local bubble of cooler gas. Recent studies of open star clusters, loose groups of stars born together, have revealed the galaxy's ongoing dispersal processes. Most clusters dissolve within a few 100 million years, their stars scattered across the disk by gravitational interactions. The Hyades cluster, visible to the naked eye in Taurus, is dissolving right now, its stars spreading out like dandelion seeds on a cosmic wind. Our own Sun was probably born in such a cluster, its siblings now scattered across the galaxy. The discovery of counter-rotating stars in the galactic disk tells stories of ancient collisions. These retrograde stars orbit backward compared to the majority, likely captured from galaxies that merged with the Milky Way from the wrong direction. They're like cars driving the wrong way on a cosmic highway, permanent reminders of violent encounters in our galaxy's youth. Some regions have so many counter-rotating stars that they form their own distinct disk within a disk. The mapping of high-velocity clouds falling into our galaxy has revealed an ongoing cosmic rain. These clouds, containing millions of solar masses of gas, are the galaxy's way of staying young. Without this constant infall of fresh gas, star formation would have ceased billions of years ago. We're witnessing cosmic recycling on the grandest scale, gas expelled by ancient supernovae in satellite galaxies now falling back to fuel new generations of stars. The realization that spiral arms are traffic jams rather than material structures revolutionized our understanding. Stars and gas clouds enter the arms, slow down due to increased gravity, pile up, then exit the other side. The arms themselves rotate at a different speed than the stars, like waves of congestion moving through cosmic traffic. This density wave theory explains why spiral patterns persist for billions of years instead of winding up like a watch spring. The discovery of resonance zones in the galaxy reveals a hidden mathematical order. At certain distances from the center, orbital periods form simple ratios with the rotation of the spiral arms or galactic bar. These resonances can trap stars, creating ring-like structures, or scatter them, creating gaps. It's like finding that our cosmic city was built on a grid of invisible mathematical relationships that shape where stars can and cannot thrive. The detection of gamma-ray heartbeats from the galactic center has added yet another dimension to our understanding. These periodic bursts of high-energy radiation, pulsing every 76 minutes, might come from a binary system where a star orbits close to the central black hole. It's as if our galaxy has a literal heartbeat, a cosmic pulse that we can detect from 26,000 light-years away. This discovery reminds us that even in the chaotic environment near a supermassive black hole, orbital mechanics creates clockwork precision. One of the most stunning revelations is the galaxy's lithium problem. According to Big Bang nucleosynthesis, there should be 3 times more lithium in old stars than we observe. This cosmic accounting error has puzzled astronomers for decades. Recent surveys across the galaxy show this lithium deficit is universal, suggesting either our understanding of the early universe is incomplete or some unknown process destroys lithium in stars. It's like auditing the galaxy's books and finding that the numbers don't add up. The discovery of stellar graveyards, regions where ancient white dwarfs have cooled to near invisibility, has revealed the galaxy's hidden population of stellar corpses. These black dwarfs, theoretical objects so cold they emit no light, might already exist in our galaxy's oldest regions. Billions of dead stars could be drifting through space, invisible to our telescopes, a dark population outnumbering living stars. We're surrounded by cosmic ghosts we can barely detect. Recent observations of the galactic halo's rotation have overturned long-held assumptions. Rather than being stationary or slowly rotating, parts of the halo spin in the same direction as the disk, while other parts rotate backward. This complex rotation pattern suggests our galaxy's formation was far messier than simple collapse models predicted. It's like discovering that different floors of a building rotate in different directions. It shouldn't be stable, but somehow it works. The phenomenon of galactic seismology, using stellar oscillations to probe the galaxy's interior, has opened a new window into cosmic structure. Just as earthquakes reveal Earth's interior, stellar quakes detected by missions like TESS and Kepler tell us about conditions deep inside stars and, by extension, different regions of the galaxy. We can literally take the galaxy's pulse by listening to its stars ring like bells. The discovery of fossil galaxy groups within our own galaxy challenges the traditional view of galactic cannibalism. Rather than being completely digested, some consumed galaxies maintain their identity for billions of years. The Helmi stream, Sequoia galaxy remnants, and Gaia Enceladus structures are like undigested meals in the galaxy's stomach. These fossils preserve information about galaxy formation from the universe's youth. The mapping of dust lanes throughout the galaxy has revealed a hidden architecture of extinction and reddening. These cosmic curtains don't just block light, they process it, absorbing blue light and re-emitting it in infrared. The galaxy glows differently at different wavelengths, like a cosmic mood ring changing colors. Understanding this dust distribution is crucial for accurate distance measurements and for finding hidden stellar populations. Recent studies of binary star systems have shown that most stars aren't alone. Over half of all Sun-like stars have companions, and for massive stars, the fraction approaches 100%. These cosmic partnerships affect everything from stellar evolution to planet formation. When we map the galaxy, we're not just mapping individual stars, but complex gravitational dances between stellar partners, each system a miniature galaxy of its own. The discovery of the galaxy's X-ray chimneys, vertical structures of hot gas extending from the galactic center, reveals yet another energy transport mechanism. These chimneys, detected by the E-Rosita telescope, might be exhaust vents for the galaxy's central engine, channeling energy from the supermassive black hole and surrounding starburst regions into the halo. It's industrial-scale cosmic engineering that we're only beginning to understand. The chemical tagging of stars, using detailed composition analysis to identify stellar siblings, has revolutionized our ability to trace stellar origins. Stars born in the same cloud share chemical fingerprints more unique than human DNA. By finding these chemical families scattered across the galaxy, astronomers can reconstruct the galaxy's assembly history star by star. It's like doing genealogy for suns, tracing family trees that span billions of years. The realization that our galaxy has seasons, periods of enhanced star formation triggered by spiral arm passages or satellite galaxy interactions, changes how we view cosmic time. Right now, we're in a relatively quiet period, but evidence suggests more active epochs in the past and future. The galaxy's seasonal cycles operate on 100-million-year timescales, making human history less than a blink in cosmic terms. The discovery of tadpole galaxies being transformed by ram pressure as they fall into our galaxy reveals the violent processes shaping galactic evolution. These galaxies, with long tails of stripped gas streaming behind them, are being transformed from spirals into ellipticals by their passage through our galaxy's hot corona. We're witnessing galaxy evolution in real time, catching cosmic metamorphosis in the act. The revelation that our galaxy produces antimatter naturally has profound implications for physics and cosmology. Positrons, antimatter, electrons, stream from the galactic center in numbers that dwarf any particle accelerator on Earth. These antimatter particles annihilate with regular matter, producing gamma rays we can detect. The source might be dark matter annihilation, black hole jets, or exotic stellar processes we don't yet understand. Our galaxy is a natural antimatter factory operating on scales that humble human technology. Recent discoveries about the galaxy's merger history have revealed we're living in the calm between storms. The last major merger occurred 8 to 10 billion years ago, but the next one is already scheduled. In 4 billion years, Andromeda will collide with the Milky Way in a cosmic dance lasting billions of years. But even now, we can see the gravitational bridge forming between the two galaxies, streams of gas already connecting us to our future dance partner. We're not just discovering our galaxy's size, we're previewing its transformation. The phenomenon of galactic feedback, how star formation and black hole activity regulate each other, shows our galaxy is a self-organizing system. Too much star formation heats the gas, shutting down further starbirth. Too little activity allows gas to cool and collapse, triggering new stellar generations. This cosmic thermostat has kept our galaxy in a sweet spot for billions of years, neither burning out in a starburst nor fading into darkness. It's nature's own regulatory mechanism operating on galactic scales. The discovery of ultra-diffuse regions within our galaxy, areas with so few stars they're nearly transparent, challenges our understanding of galaxy structure. These cosmic voids within the disk might be cleared by supernovae, shaped by magnetic fields, or simply regions that never accumulated enough matter to form stars. They're like holes in the cosmic fabric, windows through which we can peer into the depths of intergalactic space. Recent observations of stellar streams have revealed that our galaxy is surrounded by a cosmic spiderweb of disrupted satellites. Over 100 distinct streams have been identified, each one the remains of a cannibalized galaxy or star cluster. These streams don't just orbit randomly, they form a complex, interconnected network that reveals the galaxy's gravitational structure in exquisite detail. We're living inside a cosmic web woven from the remnants of dead galaxies. The mapping of molecular hydrogen, the galaxy's primary star-forming fuel, has shown that our cosmic fuel tank isn't evenly distributed. Giant molecular associations contain enough gas to form millions of stars but remain quiescent for millions of years before suddenly bursting into activity. Understanding what triggers these cosmic engines to start is one of astronomy's great mysteries. The galaxy is full of potential waiting to be realized. The discovery that cosmic rays can influence star formation adds another feedback mechanism to galactic evolution. These high-energy particles ionize gas, affecting how it collapses to form stars. In regions of intense cosmic ray flux, star formation can be suppressed. In quieter regions, it proceeds more efficiently. The galaxy regulates its own star formation through a complex interplay of radiation, magnetic fields, and gravity that we're only beginning to unravel. Recent studies of the galactic bar's influence have shown it's not just a structure, but a cosmic engine driving gas flows throughout the inner galaxy. The bar funnels gas toward the center, feeding both star formation and the central black hole. It creates resonances that trap or scatter stars, sculpting the galaxy's inner architecture. This rotating cosmic lever has been shaping our galaxy's evolution for billions of years. The phenomenon of stellar rejuvenation in dense environments reveals that even old stars can get a new lease on life. In globular clusters and the galactic center, close encounters and collisions can strip away outer layers, merge stars together, or transfer mass between companions. These cosmic facelifts create blue stragglers, millisecond pulsars, and other exotic objects that shouldn't exist according to simple stellar evolution. The galaxy has ways of recycling even its oldest inhabitants. The discovery of phase transitions in the interstellar medium shows that space between stars isn't empty, but filled with a complex, multi-phase fluid. Hot ionized gas, warm neutral gas, cold molecular clouds, and cosmic rays all coexist in a delicate balance. Shocks from supernovae and stellar winds drive gas from one phase to another, creating a cosmic weather system of unimaginable complexity. We're living inside a vast, turbulent atmosphere that spans hundreds of thousands of light years. The realization that our galaxy's dark matter halo isn't smooth but clumpy has profound implications for physics. These dark matter subhalos, ranging from Earth mass to dwarf galaxy mass, roam invisibly through our galaxy. When they pass through the disk, they might trigger star formation or disrupt planetary systems. We're surrounded by invisible structures that we can only detect through their gravitational effects, cosmic icebergs in a dark sea. The mapping of stellar ages across the galaxy has revealed waves of star formation propagating outward from the center. Like tree rings recording climate history, these age patterns preserve the galaxy's formation history. The oldest stars in the halo remember when the galaxy was just beginning to assemble. Younger populations in the disk trace subsequent waves of gas accretion and star formation. We can read the galaxy's autobiography written in the ages of its stars. As we stand at the threshold of this new understanding of our galactic home, the numbers become almost incomprehensible. 200,000 light years across the stellar disk, 900,000 light years including the dark matter halo, 1.5 trillion solar masses, 2 billion stars mapped with precision. These aren't just statistics, they're the dimensions of our cosmic neighborhood, and they've grown so dramatically that we need to completely reimagine our place in the universe. The technological symphony that revealed these truths is equally astounding. Ground-based telescopes in the Atacama Desert pierce the darkness with adaptive optics that cancel out atmospheric turbulence. Space telescopes orbit above our atmosphere, capturing light that has traveled for billions of years. Radio arrays spanning continents work together as planet-sized instruments. Each photon collected, each data point analyzed, adds another brushstroke to our portrait of the galaxy. We've turned our entire planet into an eye gazing at our cosmic home. But perhaps the most profound discovery is that size alone doesn't capture the Milky Way's true magnitude. It's the complexity, the interconnectedness, the sheer dynamism of our galaxy that takes your breath away. Every star influences its neighbors through gravity. Every supernova enriches the next generation. Every merger adds new chapters to the story. We're not living in a static cosmic city, but in a living, breathing organism that has been evolving for 13 billion years and will continue evolving for trillions more. The implications for our cosmic perspective are staggering. If our galaxy is this vast and complex, and it's just one of 2 trillion galaxies in the observable universe, then the total scope of existence is beyond human comprehension. Yet here we are, arrangements of atoms that have become conscious, capable of measuring and mapping the very galaxy that gave birth to us. The universe has evolved eyes to see itself, and those eyes belong to us. Recent philosophical discussions among scientists have grappled with what this means for humanity's future. If our galaxy is 50% larger than we thought, that's 50% more resources, 50% more planets, 50% more chances for life. The Drake equation, which estimates the number of communicating civilizations, might need to be revised upward. We could be living in a galaxy teeming with life, separated only by the vast distances that light takes centuries to cross. The discovery process itself tells a story of human ingenuity and cooperation. Thousands of scientists from dozens of countries worked together to map our galaxy. They shared data freely, checked each other's work, and built on discoveries spanning generations. The Gaia mission alone involved over 400 scientists and engineers. This isn't just astronomy, it's humanity at its best, working together to answer fundamental questions about our existence. The journey from ancient sky watchers who saw a river of light to modern astronomers mapping billions of individual stars represents one of humanity's greatest intellectual achievements. Each generation built on the last, from Galileo's first telescopic observations to Herschel's attempt to map the galaxy to Shapley's realization that we're not at the center to today's precision measurements. We stand on the shoulders of giants who themselves stood on the shoulders of giants. What strikes me most is how personal this cosmic story becomes. Those calcium atoms in your bones. They were forged in a supernova explosion perhaps 8 billion years ago, traveled through interstellar space for billions of years, became part of the cloud that formed our solar system, were incorporated into Earth, cycled through countless organisms, and now help you stand and walk and dance. You are literally made of Milky Way matter, shaped by Milky Way processes, thinking Milky Way thoughts. The future of galactic exploration promises even more revolutionary discoveries. The Nancy Grace Roman Space Telescope will survey billions of stars with infrared vision. The square-kilometer array will map cosmic magnetic fields in unprecedented detail. The extremely large telescope will resolve individual stars in galaxies millions of light-years away. Each new instrument is like developing a new sense, revealing aspects of our galaxy we couldn't imagine before. But perhaps the most important message is this: we belong here. Not just on Earth, not just in the solar system, but in this magnificent galaxy. Every atom in our bodies, every thought in our minds, every emotion we feel is part of the Milky Way's ongoing story. We're not separate from the cosmos, we're expressions of it. When you look up at the night sky, you're not looking out at something foreign and distant. You're looking at your extended family, your cosmic ancestry, your home. The true size of the Milky Way isn't measured only in light years or solar masses. It's measured in the billions of years of history written in its stars, in the complex chemistry that made life possible, in the precise balance of forces that allow planets to orbit peacefully for eons. It's measured in the fact that out of all this vastness, on one small planet orbiting an ordinary star, in an unremarkable spiral arm, matter organized itself into beings capable of love, wonder, and the desire to understand. So the next time you're outside on a clear, dark night, take a moment to really see the Milky Way. That river of light isn't just a pretty sight. It's your home galaxy, vastly larger and more magnificent than we ever dreamed. Each point of light is a sun, possibly warming planets, possibly nurturing life. And you, standing there looking up, are the universe contemplating itself, a child of the stars coming to know its cosmic family. We've discovered that our galaxy is not just big, it's enormous, not just old, it's ancient, not just complex, it's magnificently, beautifully, almost impossibly intricate. And in all that vastness, in all that complexity, atoms came together to create you. You are the Milky Way thinking about the Milky Way. And that might be the most profound discovery of all. If you are still watching, make sure to subscribe to the channel and give a thumbs up. Your support means a lot to me, and if you enjoyed this video, I am sure you will love this other at the left side of the screen. How big is the universe? In this video, discover the true scale of the cosmos, from the size of Earth and our solar system to the Milky Way, superclusters, and much more. See you there.